Good good afternoon. Hello.
Hello, good afternoon.
Good afternoon. I'm Raffaele Longo
Yes.
from the
Okay.
University of Salerno.
Thank you. I glad when you. Are you ready to presentation?
Yeah.
Okay. Welcome to the 4th International Symposium on Multidisciplinary Studies and Innovative Technologies. Due to COVID-19, we are holding our symposium virtually. I hope this epidemic will end as soon as possible. Let's start this session, last session of the symposium. First paper belonged to Rafael Longo. If you are ready, Mr. Rafael Longo, you can start the session.
Okay, I start. Okay. Just a second. I share the screen.
Okay. You have at most 10 minutes, please.
Okay. Okay. Can you see my screen?
Yes, I can.
Okay, perfect. Okay. Good afternoon. I'm Raffaele Longo, and today I am a PhD student in the University of Salerno. And today I'm going to present the electromagnetic characterization of polycaprolactone electrospun nanofibers filled with magnetite nanoparticles. Electrospinning is a process that allows to produce nanofibrous materials that go in a range from hundreds of nanometers to thousands of nanometers. And through the design and control of the product characteristic, it is possible, and through setting several parameters, it is possible to obtain math and networks, just like here the one represented in the picture. This type of network are particularly appreciated in the biomedical field and in the biomedical engineering, in particular for two aspects: for the tissue engineering and for the drug delivery. Being employed in the biomedical field, usually the materials used are biomaterials. The biomaterials can be of two types: can be natural biomaterials that present an excellent biocompatibility but poor mechanical properties, or synthetic biomaterials that present a good biocompatibility and good mechanical properties, just like the polycaprolactone. Our group is focused on the research, and our project of research is focused on the research of cancer. Why to research on cancer? Well, cancer is the second cause of death all over the world, and it is responsible of the 17% of all the global death. Here in this table, I have briefly summarized the survival rates at 5 years by the diagnosis in the 50s and nowadays, more or less. As you can see, for the breast cancer, for example, the survival rate has raised from the 60% to over the 90%, from the leukemia from the 10% to over the 60%, and so on. So this type of research have a real effect on life of people. In particular, for the cancer treatments, are very employed also nowadays the electromagnetic stimuli and electromagnetic radiations. Here I have brought the spectra, the electromagnetic spectra, and as you can see, in each range we can find more or less an application for the gamma and X-rays. You can find the radiotherapy, the radiography, down to the very, very high wavelength where we have the electroporation, the stimulation, the electrostimulation. So our strategy is to use these innovative materials with the active filler in combination with an electromagnetic radiation for the fight against cancer. In particular, today I'm going to present the production of polycaprolactone electrospun membranes loaded with magnetite nanoparticles. I'm going to show the morphology characteristic, the thermal stability, and the electromagnetic characteristic, and the biological performance. Here we have in particular, the nanocomposite membranes produced are composed by magnetite nanoparticles functionalized with citric acid, here, as you can see here in the picture. The average diameter of these nanoparticles is around 5 nanometers, more or less. And we have produced the membranes from 0 to 10% of magnetite percentage in the matrix of PCl. It is not simple to obtain this nanocomposite membrane. In fact, we needed a phase of optimization of the process parameters and the solution parameters mostly. As you can see here, we have obtained successfully membranes for 14% of polymer concentration, but just raising these values from to the 17.5%, it is possible to see how the defects are well evident into the mat. So as regard the produced membrane with the 14% of polymer concentration, here you can see that the membranes, the SEM analysis of these membranes are very homogeneous, and here I reported the curve distribution of the fiber diameter. These curve distribution are, most of the fiber diameters are in a range from 400 nanometers to 1500 nanometers, more or less. And this curve became wider by raising the amount of nanoparticles inside. As you can see by the EDS analysis, not only the nanoparticles are inside are into the system, but here, as you can see, are along exactly along the nanofibers, as you can see. Then, to study the morphology even better, we have decided to analyze the dimensions of pore through a processing of the images via MATLAB, and converting the images in binary code. In binary code, as you can see, we obtained a curve distribution of the pores diameter, knowing in this way that by raising the amount of nanoparticles inside, we increases also the average diameter of the pores. Then, by the thermogravimetric analysis, we have noticed several things. Firstly, just comparing here the two most different curves from the 0 and the 10% nanocomposite membrane. As you can see, there is anticipation of the thermal degradation for the nanocomposite membranes, and moreover, there is this point of flex that is also confirmed by the derivative of the thermogravimetric analysis. And this step of the double degradation is due to the degradation of the citric acid it is attributed to the degradation of the citric acid in the magnetite nanoparticles. So, however, the inclusion of these magnetic nanoparticles inside is not a problem as regard the thermal stability, since these membranes are applied for a biomedical application. So their thermal stability is up to 350 degrees, more or less. So we are quite higher than the threshold that we needed. These membranes have also been applied with to a biological test to see their anti-tumor, their cytotoxic effect. In particular, for 3 tumor cell lines, the cervix uterine and the 2 lines of melanoma. As regards the cervix uterine cell viability, you can see here in the picture how raising the amount of membranes to the ratio amount of membrane to cells treated, you can see how the cell viability decreases. In fact, and so down to almost the 40%. And similar results are also reported for the 2 lines of melanoma. In particular, from 2 to 10% of magnetite nanoparticles. Here, for the first line of melanoma, we have a cell viability of the 50%, more or less, and similar results also for the other one. And moreover, we also notice a dose-dependent cytotoxic effect for these types of membrane. Then, in order to understand if these membranes can be applied in combination with an electromagnetic, with the electromagnetic stimuli, we have also decided to analyze and to characterize these membranes from an electromagnetic point of view. In particular, we have just focused on the electrical, characteristic, the complex permittivity, and so in this way also the electrical conductivity. In particular, comparing the results of the PCL non-electrospan and the PSAL electrospan, we can see the first differences. The electric permittivity in a range of frequency from the megahertz to the gigahertz, we can see that the electric permittivity of the PCL electrospan is almost the half to the compared to the non-electrospan membranes. And similar results are also for the conductivity. It is probably due to the fact that the network of the PCL electrospan is not a continuous network. There is void inside, as you can see by the morphological images that displayed before. And so probably this high amount of air causes a big difference between the performance, the characteristic of the non-electrospan and the electrospan membrane. Moreover, also analyzing the nanocomposite systems, as you can see here, by raising the amount of magnetite nanoparticles, increases as well the electric permittivity. So, in conclusion, we have developed electrospan membranes and loaded with magnetite, with functionalized magnetite. We have analyzed their characteristic by a morphological and thermal point of view. We have tested them already, and they showed an high anti-tumor activity, so tested in a biological environment. And we started an electromagnetic characterization in order to evaluate their potential application in a biological environment in combination with an electromagnetic stimuli. Thank you for your attention.
Thank you for your presentation. Dear participants, do you have any question about this article? Okay, no question. Thank you very much again. I wish you success in your career. Hope to see you, Mr. Rafael Longo.
Thank you very
much. You and two friends is online now. Is there any participant with a paper in this session? Fatima Ajjal? You have a paper?
Sorry?
No, I asked to Fatima Ajjal.
Ah, okay, sorry.
Mrs. Fatima Ajjal. Okay, Said Ahmed Rahim is online. Saab Hazim Ahmed is online. Mr. Saadaldin Rashid Ahmed is online. Petya Byalmarkova is online. Okay, let's wait for a while. Maybe they could be online. Is there any participant with a paper in this session? Mrs. Fatima Adjal, can you hear me? You have a paper in this session?